Alright, let's continue. Your schedule's already been determined now. Too late. No sense whining.
It's never too late.
That's
And it's never too late. It's too late for it to be useful to change. Okay. Modular arithmetic is the second section. And maybe some brief conversation about arithmetic in general. Arithmetic in general is somewhat contextual as to whether or not we can do it. So if we go all the way back to one of the simplest systems for us to work with, it's the natural numbers, the counting numbers. You tell kids, count with your fingers, and so 1, 2, 3, 4, 5. They learn how to count. Pretty soon they learn how to add with the natural numbers. And then they learn that multiplying is just doing addition really, really fast, right? And then you got the concept of subtraction. You want to introduce subtraction to it. And you want to do something like 3 minus 5. Well, what's 3 minus 5? Doesn't really make sense unless we go outside the scope of the natural numbers and introduce the integers. And that's a harder concept for kids to grasp when they first come across it. -2, what's -2? Show me -2. Understand 1, I kind of understand 0. What's negative fingers? Yeah, the kids have a hard time with this. And so you have to expand the context that you're talking about subtraction on. You have to expand the context of the numbers you're talking about to make subtraction start making more sense to you. Similar thing happened with division, obviously. So you learn subtraction, then division comes along, and you were probably told something weird like it's subtraction except for really fast, I don't know. But the point is, when you learned how to do division, you could only do it in very specific cases. You knew how to do 9 divided by 3. You even knew how to do -9 divided by 3. But then when I said, what's 9 divided by 4? You were at a loss. And you had to do like the remainder thing that we talked about before. Or you have to change the context that you're talking about when you're doing your arithmetic, and switch it to the rationals. And once you got to the rationals, you said, oh, it's just 9/4. There's nothing wrong with that. That's a perfectly fine number. So that is talking about arithmetic on those different systems of numbers. And what do we mean by arithmetic? We mean flat out multiplication, addition, subtraction, division. Arithmetic. That's all arithmetic is, and we're just looking at arithmetic on different sets of numbers. So we're going to be looking at a really, really, really simple set of numbers, and it's going to be this z sub n group. I think I've used this notation before. I don't remember if I have. But what is z sub n? It's all the integers. It's the first n naturals. That's all it is. The first n naturals. Okay. So it's 0, 1, 2, 3, 4, 5, 6, all the way up to n minus 1. If you do z sub 10, then that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The first 10 numbers. It's the first 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The first 10. Starting at 0. It's just a symbol. And some people don't include the zeros in the naturals. Some people do. In this class we included 0. So it might make sense in this class to do it that way. But for example, in our calculus class, 0 is not a natural number. It's just a matter of how you define the set.
How can you do math if 0 is not
It's still a number. It's still a real number. It's still an integer. It's just some people define the natural numbers to have 0. Some people define it not to have 0. And to just be 1.
Universal if that's not true? I mean, if 0 is inside and 0 is not natural.
I can come up with my own symbols left and right for how I want to use them and still apply the same old math to it. They're not treating 0 different than they treated 0 in the past. They're just saying, are we going to include it with this symbol n? Does this have the 0 in there or not? It's not changing what 0 is. It's still the additive identity. It's still what 0 is. It's just how we use that notation. Anyways, so we are going to be looking at arithmetic on sets like this. That's what we're going to be doing. We're going to be adding, subtracting, multiplying, and dividing numbers on little teeny sets. Not even all the integers, just these little teeny sets. That's it. That's this whole chapter, or this whole section. Super easy, right?
I guess.
Totally.
Alright, let's do it then. If it's so easy. So let n be any positive integer, and let a and b be two elements of z sub n. You with me so far?
Yeah.
Grab two things out there called a and b. Since we're doing a different type of addition, since it's addition on this specific set, we're going to use these weird symbols for what we mean by this addition. What do we mean by a plus b? We mean a plus b mod n. Why mod n? That keeps it in this set.
So mod n does nothing. You just
What does mod n do? It gives you the remainder when you divide by n. Your remainder is always less than n. The biggest it can be is n minus 1. It can be 0, 1, 2, 3, 4, 5, 6, all the way up to n minus 1. Can't be any bigger. Has to be one of those numbers. Similarly, we define a times b to be a times b mod n. This we call modular addition, and this we call modular multiplication. Okay? Okay. And that's how we define it. Nice and simple, right? Keeping everything's in terms of the set. So let's do some basic arithmetic to make sure you got it. What's 5 plus 5? 10 mod 10, though. Oh, sorry, should have specified. Let n equal 10. So what is our set equal to? Z sub 10 is equal to 0, 1, dot, 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 all the way up to 9. Right?
Yeah.
So 5 plus 5 is
0.
0. What are you saying? 0, 1, 10.
It does be 0, 0.
What is 5 plus 5 with regular addition?
5. I mean 10.
What is the remainder when you take 10 and you divide it by 10?
0, but why are you dividing?
That's what mod means.
A plus b in modular arithmetic is a plus b in normal arithmetic mod n. Our n is 10. So 5 plus 5 is 10. 10 mod 10 is
Okay, I get it now.
wonderful. So 5 plus 5 is 0, right? 2 plus 2?
4 mod.
4. 5 plus 8?
How is that 4? 3.
All right. What's 2 plus 2?
4.
What's 4 mod 10? Carry the 2.
2.
4 mod 10 is 2.
Think remainder.
I am.
What is the remainder when I do 4 divided by 10? It's equal to 0 with a remainder of 4. How many times does 10 go into 4?
0.
0 times. You can fit 0 tens in 4.
I'm
Okay.
thinking of it backwards.
You would go back and think exactly how you thought as a third grader about all arithmetic, and that will help you. We're going back to the basics. Okay. So now, Peter, what's 5 plus 8?
3.
3. Does anyone disagree with Peter? 5 plus 8 is 3.
Yeah.
Let's do it again. Back in normal town.
Okay.
What's 5 plus 8?
13.
Mod 10.
Oh, it's 3 because Peter said it.
13 divided by 10 is equal to 1 with a remainder of 3.
Oh, okay. I'm sorry.
No, that's fine. This will be confusing to begin with. No way around it. Okay. So we figured this one out as 3. And what is 9 plus 19?
8.
Does anyone disagree with that? For the next 30 seconds, I will give extra credit to whoever can figure out why that answer is wrong.
But it's
I
right.
can't even figure out what 9 plus 19 is.
Time's up.
Alright.
Undefined. A and B have to be members of the set. We did not define it for
Oh my
where
God.
A and B is not members of the set. And you're going to have a homework problem, and every year students ask me, why is it wrong? Where the teacher asks you to solve a problem, he says, hint, it's not, in this case, 8. And students struggle with it, and struggle with it, and struggle with it, and no one ever figures out it's undefined. So in this case, undefined. Okay, so there's like the one gotcha with these, I think. Outside of that, I think they're pretty straightforward. 5 times 5? 5. Right? 2 times 2? 4. A little hesitant. This side of the room. 5 times 8?
0.
You're not this side of the room. 0. Lastly, 9 times 9? 1.
Oh, good job, I knew.
You do that one? Alright. Are we confused by what's going on?
No.
Okay. You're just not answering? Need to start throwing stuff? Had to throw it all at him. You can't throw stuff at a girl. And Peter keeps answering. Yeah, throw stuff at you for answering. Alright, moving on. So, think you're comfortable with addition and subtraction, or addition and multiplication. Now we need to move on to subtraction. Oh, wait, this is a homework problem that you have to do. Pretty simple. Let A and B be in Zn. Your job is to prove that A plus B is always in Zn, and A times B is always in Zn. Hint. Is it obvious to everyone how you're going to do this problem now?
No.
No? When I take two things, add them together, I get some number, but then I mod it by n, what does that mean? It means the remainder when you divide by n.
It's less than.
It's the remainder when you divide by n. A equal QB plus R. Now in this case, RB is n, and it gives you the remainder. What do you know about the remainder always and forever? 0 less than or equal to R less than n. What is Zn? All the integers satisfying that. Easy? Now it all makes sense? Easy as pie? You know how you're going to prove that? And we call that a closure property. An operation is closed on some set if, when you apply the operations to two members of the set, you still get a member of the set. Those of you that did logic might remember we did basic proofs like this for arithmetic. Exact same type of thinking here. And the proofs for that and the proofs for that aren't that different. Anyways, so addition and multiplication are closed operations. Let me give you an example of an operation that's not closed. Subtraction on the natural numbers is not a closed operation. If I take two natural numbers and I take their difference, or if I take one natural number and I subtract another natural number, I'm not guaranteed to get a natural number. What we're saying here is if you take two elements of Zn and you modularly add them together, you're guaranteed to get an element of Zn. That's what you're proving. Similarly with multiplication. Those are closure properties. Not all operations have them. Operations for a given set. So you're going to prove it in this case. Does that make sense? And why that's not necessarily something that's just always given. Another example, division is not a closed operation on the integers. Well, it's 4 divided by 3, not an integer. That's what it is. Good?
Yep.
Okay. So you're proving that those two things are closed, basically. And hint, use the definition, the fact that's mod n. Alright. And this is not, by the way, this is not congruent mod n, like we were using way, way back. This is mod n the operation. So that's not equivalent, that's equals. Okay, make sure that's right for you. Alright, where are we at? Somewhere down here. Okay, bunch of properties that these things satisfy. Properties we all know and love, and that we would expect these things to have. So let n be some natural number where n is greater than or equal to 2. I don't know why I said natural number instead of positive integer. Same thing though, it's a positive integer greater than or equal to 2, or a natural number greater Oh, we just want to make sure that 0 and 1 are in our Zn. You'll see when I list properties. Greater than 2. And let A, B, and C be elements of Zn. So what does Zn look like? We don't know, but at the very least, it has 2 elements in there, namely 0 and 1. Because n is greater than or equal to 2. And the only reason we say that is because now I'm going to specify 0 and 1 down here. And now I know their elements. Okay, what are we proving? We're proving that A plus B is equal to B plus A. Or in other words, that modular addition is?
Associative.
Commutative.
Commutative.
You take a shot. And so is the multiplication. And then we're going to prove that addition is associative, and so is multiplication. And then we're going to prove what? How do we say this? That 0 is the additive identity. And then we're going to prove that 1 is the multiplicative identity. Just like we did when we were doing arithmetic back in logic. And we proved that 0 was the additive and 1 was the multiplicative identity. Okay? And then finally, what's this one called?
Distributive.
Wonderful, the distributive law. So these are all things that hold. Going through and proving all these will be kind of tedious, so we'll prove one of them. And I guess I picked associative. So let's prove really quick that addition is associative. So proof. Let n be some positive integer. In this case, we don't need it to be greater than or equal to 2. We only need the greater than or equal to 2 for referencing 0 and 1. So we can just say some positive integer. Comma. And let A, B, C in Zn. Those might all be the same number. They might all be different numbers. All we know is that they're all elements of Zn. Then, what are we proving? We're proving that A plus B plus C is equal to A plus B plus C. Understand what we're trying to prove?
Yep.
Okay, so let's do it. Now, how do I want to start? Just observe, I guess. Observe that, all right, A plus B plus C. Okay, this B plus C, what is B plus C? Looking back over at our definitions of B plus C, what is it?
It's B plus C.
It's B plus C
Mod n.
mod n. So this B plus C can be any number, B plus C, times any multiple of n. All the numbers that this could possibly be are of the form this. And this is going to be the weirdest part in doing proofs with these things. So let's make sure that this one piece makes sense, and I think the rest will come together. B plus C plus some integer multiple of n. These are all the numbers in our regular integers that give us B plus C in this modular addition. If it's of this form, then when we go to our regular integers that we know how to work with, it must have been in this form.
Y plus kn.
Plus kn plus any integer multiple of n. So let's go into how could we say this to help it make sense? Look, going back over here, I could have gotten, how can I make this make sense? Need an example that will work. So B plus C, let's see, we'll just pick two numbers. Pretend we're in mod 10 for a second. So let's do 8 plus 8 is equal to what?
4.
6.
Oh, I was thinking times.
8 plus 8 is equal to 6, right? But we also have, let's see another way that we can get it. 3 plus 3 is equal to 6. So these are two ways of expressing the exact same value, right? The difference is that this one, when we do it in regular addition, is 3 plus 3 plus 10, whereas this one was just 3 plus 3. Okay, let's see. Now I don't have a good way to say this, so let's just say that this was my B and my C for a second. So we have A plus now, 8 plus 8 plus, in order to get that 6 out, I need plus a negative 10. Some integer multiple of 10. Which would have been the exact same thing as if I had just done 3 plus 3. These are both the exact same number over here, but this, when we plug it in, gave us 16, and then we'd have to subtract 10 to get the same number that we got here, which was just 3. So to convert between these two things, all our answers are within a multiple of 10 of each other. That's what I'm trying to say. Maybe that's a better way to say it. Notice that this and this are the exact same thing, right? They're both just 6. So this and this are the exact same thing. But when we put them over here, notice now they're drastically different things. But they are still the same within some factor of 10. So I can add some multiple of 10 to this to get this, or I can subtract some multiple of 10 from this to get this, and then we get the same thing. So if we did all the numbers that come out the same way, then they're always going to vary by some multiple of n. Maybe that's the way to say it. We'd have to add some multiple of n to get them to their most reduced form. Maybe that's another way to say it. But another way to think about it is, we added two numbers together and then we modded them by n, or we divided them by n, or we took away multiples of n to get the remainder. Well, just put the multiples of n back and you didn't do anything to it now. There's another way to think about it. Okay, that's probably the best way to think about it. Okay, so now, let's see, that's fine. So that is equal to that is equal to, now I need to do the modular arithmetic of this thing and this thing. Okay, well, is that how I want to say that now? Or will I lose you again? Notice that this only applies when we get this in its most reduced form. We have to keep taking away multiples of n to make this modular addition still work. So we need this in its most reduced form.
What do you mean it's most simplest?
Okay, let's go back to this. 8 plus 8 and 3 plus 3, right? So when I do 8 plus 8 and I plug it into here, now I want a plus, pretend we're in mod 10 for a second, then I want a plus 8 plus 8, uh-oh, I'm in trouble. 8 plus 8 is 16, that's not in there. I need to subtract some multiple of 10. Okay, now I can do that. Similarly with 3 plus 3, it would have been a plus 3 plus 3. Uh-oh, I need to add some multiple of 10, namely 0. Okay, now we're good. We didn't really have to do anything on that. But we could have had to do something is the point. That make sense? Okay. There's another way to help think about it. So then, we're going to do the same thing now with the A. Right? So A is going to be this plus this, mod n. So to do that, we need to add the factor of n. So this is equal to, now a plus b plus c plus some kn plus some jn. Same thing, right? And now we're just regrouping the terms. And now we can do it in whatever order we want. So this is going to be the same thing as, sorry, let me make sure I keep this up to date with where we are, so I don't lie to you. Okay, yeah. So this is the same thing. First we'll combine like terms, of course, as a plus b plus c plus whatever you want, k and j. We can call it a different term or we'll just group them together. K plus j n, some multiple of n. And then this is equal to, let's see, where did we start? We started with the b and c group together. So now we can do a plus b, and we can throw our multiple in there. There's a fast way to do it. Rather than reworking it all the way through, we say that this is equal to this is equal to a plus b plus c mod n. Congruent to. Sorry. That now is congruent to, so we're actually just going to use a theorem that you already had. A plus b plus c mod n. And then we'll do the same thing with the other one, but let's make sure that you see that. Congruent mod n. I got it. There we go. Okay. So in evaluating this term, we could have had to mess with it by a factor of n. And then in evaluating this term, we could have had to mess with it by a factor of n. Combine your n terms together. Now this, when we do our congruence mod n, just gives us whatever this was mod n, because we know what this is mod n. It's just this term. When we take this term and we mod by n, what do we get? 0. So it's just going to be whatever these terms were when you would mod by n.
Are you saying those are congruent mod n?
Yeah, that's a congruence now.
Okay.
So this is congruent to this mod n.
How does that prove what we're trying to prove?
We're not. We showed that this is the same as this, then we showed that this is the same as this, and then they're the same. Because if two things are congruent mod n, then they're equal to each other mod n. That was a proof you did last time.
Right. Okay.
Yeah, that's why I wondered where the author was going with this. Okay? So far all we've shown is that this is the same as this. Sorry, this is congruent to this mod n. Let's summarize that in one line. Then a plus b plus c is congruent to a plus b plus c mod n. Good?
Yeah.
Okay. Then we do similar reasoning. Then, using the other one, just expanding it a little bit differently, we do, oh, that's not the one we showed. We showed, oh yeah, it is. So then we show that a plus b plus c is congruent to a plus b plus c on n. It's going to be a similar type of thinking. We skipped a step, which is redoing this for the other expression. Right? So now, since we have those two things are the same mod n, you did a proof last week. It was the one that I told you you're probably going to get stuck on. And that was the proof that a mod n equal to b mod n is logically equivalent to a congruent to b mod n. Remember that proof?
Yep.
So that's what we're using. So we showed one's congruent to the other mod n, therefore they're equal to each other mod n. Good? So that's how that proof works. Okay, so now let's move on to modular subtraction. And if you remember way back to arithmetic, how did we define subtraction?
The addition of a negative number?
That's what we did in calculus. But back in arithmetic and logic, we said we're going to define
Everything in this that's not in
a minus b is equal to the unique x such that a is equal to x plus b. It's the unique x that satisfies this equation. That's what x is. That's how we defined subtraction. And you might remember that we proved that first off there was an x that satisfied this. That was an axiom. And then we proved that there was only one x that satisfied this. So you had to prove that there was one and only one x that satisfied this equation, sorry. And so we called that x the answer to this problem. So what is a minus b equal? It equals the one and only one x that satisfies this equation. That's what a minus b equals. That's how we did it in arithmetic. We're going to do the exact same thing here. So let n be a positive integer and let a and b be in Zn. Then we're going to say that a minus b is a unique x in n, in Zn, such that a is equal to b plus x. And you might be thinking to yourself, why didn't we just define a minus b to be this thing? And you could have, and that would have been just fine. If you define a minus b to be this thing, then you would prove this thing. If you define a minus b to be this thing, then you prove this thing. So you pick one to be your definition, the other one's going to be a theorem. Make sense? So we could have used this to be our definition and prove this. We're going to use this to be our definition and prove this. Makes no difference. They're logically equivalent. Make sense? Alright, so let's do our proof. So, prove that, let's see, where are we? This one. Let n be a positive integer. And let a be in Zn. Okay, so if that's how we're going to define it, first we need to prove that there is one and only one. So then there exists a unique x in Zn such that a plus, with that kind of plus, x is equal to b. And then whatever that x is, we will now call the difference, we'll call a minus b. Oh, oops, I did it backwards. We want it to be the answer to a minus b, so we need to add b to it to get a. So such that a is equal to b plus that x. Right? So first we need to prove that there is something in there that satisfies that. Let's see. Show that we need to check that x is in Zn and satisfies that. Yep. By definition of the binary operation mod, x is a remainder when we divide a minus b by n. Oh, so he's going to jump straight to this. Okay. So let x be this magical number, which we expect our definition to be, and we'll show that it satisfies the definition. Let x equal a minus b mod n. And then, what do we know about x if it's equal to this mod this? Then, there exists some q, doesn't really matter, we won't really use the q later, but just to see the definition that we're using. So then there exists some q, such that x is equal to q times, oh wait, this divided by this, sorry. This, a minus b is equal to q times n, some integer times n, plus x, where 0 is less than or equal to x is less than n. No?
No.
X is equal to the remainder of this division.
Okay.
So when I divide this by this, I get its quotient and its remainder. So a is equal to some integer times this plus the remainder. Good? Just using that first thing we basically proved in number theory. And now x has to have the property that's between 0 and n, right? Our remainder cannot get more than what we divided by. Make sense?
Yep.
Okay. So then x is in Zn. It's an integer between 0 and n. That's what Zn is. Right?
Mm-hmm.
So we showed that x is a unique thing in there. Now we need to show, if x is equal to this, then it's in there. Now I need to show that x satisfies this equation. And then I need to show if something else satisfies that equation, it's equal to x. So we have 3 steps here. First step, if we have x equal to this, okay, it is in there. Now I'm going to show that x satisfies this equation. And then I'm going to show that if something else satisfies that equation, it's equal to x. So x is the only thing. Make sense? So, 4. Observe that maybe we'll just evaluate this side of the expression to get to there. Then there exists x. Yeah. So let's see. So observe that I need to evaluate this side of the expression and show it's equal to that. Therefore, x satisfies this. So observe that b plus x is equal to b plus, what's x? A minus b mod n. Right? Which is equal to, using our definition of addition, b plus a minus b mod n. Just using our definition directly, right? And now, it does not matter if we mod this by n here, or we wait to do all our arithmetic in mod n. It's all the same. So this is going to be the exact same thing as b plus a minus b mod n, which is equal to a mod n. But we already know that a is an element of Zn, so when you mod it by n, you still just get a.
Wait, what?
A is in Zn.
Why is that equal to a mod n?
The b's cancel.
What are you trying to prove? Because you just proved that b plus x.
I just barely showed that b plus x is equal to a.
You have that in your. You have it in your. Oh.
No. I defined x to be this thing. And I'm saying, look, if you have x equal to this thing, it's going to be the one and only x that satisfies this. So first I have x be this thing. Then I showed that x is in Zn. Right?
And then you're trying to prove it's only one in there.
In fact, we don't even really need this mod n here because we already know that x is in Zn. So modding by n doesn't change anything. So that was kind of redundant. So reducing the 2 mod n's to 1 mod n's doesn't matter, it still works. Modding by n doesn't change anything, right? Does everyone understand how if I look at the numbers, 0, 1, 2, we'll look at z sub 5, just so I don't have to write too much. If I have one of these numbers, and I mod it by 5, I'm still going to get one of these numbers.
Yeah.
In general, if I have an element out of Zn, and I then mod it by n, I still just have the exact same number. It doesn't change anything.
Oh, yeah.
Okay, there we go. Yeah, so now it's quicker. So A mod n and A are the same thing. Why? Because A is a member of Zn. So that's why these mods aren't changing anything. Okay. So now we show that x does satisfy that equation. It remains for us to show that if something else satisfies that equation, it's also x. So 5, assume by way of contradiction that there exists y in Zn such that A is equal to B plus y and y is not equal to x. And we're going to show that y is in fact equal to x, contradiction, and therefore x is unique. Everyone understand big picture what we're doing?
Yep.
Okay. So 6. Then, let's see, how are we going to do this? So then we have b plus x is equal to a is equal to b plus y, right? Which is the exact same thing as b plus x mod n is equal to a plus x mod n.
You need to.
Why
Sorry,
A?
b plus y. Right? Which means that b plus x, well, I'm showing that b plus x is the same. How am I going to get rid of my b's?
Can't you just subtract the b from both?
I don't know that I can do that. I don't know to justify it.
I was gonna say the same thing except I was gonna say.
Okay, so we're just going to have to go straight to, I thought that we were going to use congruence, but we're going to have to go straight to actually expanding these out back into real numbers. Back in regular arithmetic. So this one then is the same thing as b plus x plus, when we get rid of mod n, then to get back to where we started, we may or may not have to add some integer multiple of n. So kn is equal to b plus y plus some other integer multiple of n, maybe the same thing, maybe different, we don't know. So I'll call that j, let's just call it k1 and k2. You okay with that, to get rid of our mod n's?
Yep.
Okay. Now we can do good old-fashioned algebra. So this gives us that. Get rid of the b's. Now we can say that x plus k1n is equal to y plus k2n. Right?
Yeah.
Then when we mod both sides by n, then we're going to get x is equal to y. So then that gives us that x plus k1n mod n, we don't need parentheses there, mod n, is equal to y plus k2n mod n, right? If these two numbers are the same number, then their remainder when I divide it by n is the exact same number, right? And now, what is this same mod n? This thing's going to be 0. X was already in Zn, so this is just x. Similarly, that's 0. This was already in Zn, so its remainder when you divide by it is just y. So x is equal to y. Contradiction. There we go. Make sense?
Yeah.
We showed three things. We showed, first of all, that so we were saying x equal to that thing is going to be the x that satisfies this. We showed 1, that x was in Zn. 2, that x satisfies that equation. And then 3, that if anything else satisfies that equation, it's really just x. Make sense? Okay. Let's see. This one now. A minus b mod n. I don't know why we'd prove that. We just really showed that if we let x be that thing, then this is the case. So we said that x equal to this thing is a unique solution to this equation. Maybe we'll get something different. Let's do it. Probably keep my lets the same. That. Erase this. So, let that and let that. Then, A minus B is equal to A minus B mod n. Right? That's what we're trying to prove. So how do we do this? Go back to our definition of this. What is this? This is the unique x that makes this true. Right? So, observe that, by definition, this thing is this x that makes this true. So I know that this thing plus, so there's my x, plus b, is equal to a. But I want that to equal to a minus b mod n. And I don't want it all on the same side. I want to get just the x. One sec, let me get just my x. We need to show that a minus b mod n is in Zn, and 2, that if x is equal to a. We need to show 1, that a minus b mod n is in Zn. We already showed that. And then 2, if x is equal to a minus b mod n, then a is equal to b plus x. Oh, because x is a unique thing that makes that true. Okay. I guess that works. So let's go over the 2 steps of the thing, because we're going to make x equal to just our a minus b mod n. So, I guess we don't have an x up there. So 1, let x, it's going to be very similar to our previous proof that we just did, equal a minus b mod n. First thing we need to show is that x is in Zn. Second thing I'm going to show is that x satisfies this equation. We know that one and only thing in Zn satisfies this equation, namely this here. Therefore, they're the same. So we're going to start with x equal to this. I was coming at with trying to make x equal to that thing. Okay. So you understand what we're doing? I'm saying x is equal to this. I'm trying to get that x is equal to a minus b. How will I show that x is equal to a minus b? I need to show that a is equal to x plus b. Right? What is this? It's the unique x that makes this true. So if I can find the unique x that makes this true, then we're done. So first I need to show that this thing is in Zn, and then I need to show that it satisfies this equation, and therefore it's this. Which is basically exactly what we just did with the previous proof, but we'll do it all over again. So I'll let x equal that. 2. Then x is a remainder when we divide by n. So then I'm going to skip straight to this, and hopefully you understand it. Then x is between 0 and n. If x is a remainder of this division when you divide by n, then the remainder has to be less than n, and it has to be a non-negative number. So that gives me x is in Zn, right? So we showed x is in Zn. Now we need to show that x satisfies this equation. Observe that, let's see, we want x plus b or b plus x. We just need to show that's equal to a. So b plus x is equal to, ultimately I'm trying to show it's equal to a. Well, it's equal to b plus x we just barely showed that, well, no, that's still fine. And this is equal to b plus, we'll still keep that in there, a minus b plus some multiple of n, which is equal to, now taking this one, we don't need parentheses, b plus a minus b plus kn all mod n, just using the definition of this addition. This addition is that plus that mod n, which gives us this. B's go out, and so we're left with a minus or a plus kn mod n. Well, when we mod n, that's just going to go to 0, and all we're going to be left with is a mod n, which is just a since a is in Zn. And we're done. We show that b plus x is equal to a. Therefore, x is a unique integer that satisfies this equation. Therefore, x is a minus b. Okay, so from here on out, anytime you see this, you're just going to interpret it like this. And that's perfectly valid. Okay. So we've got addition, we've got multiplication, we've got subtraction. Finally, we need division. And division, as predicted, is always a big old pain. So let's see why division is a big old pain. In ordinary arithmetic, if a times b is equal to a times c, then b is equal to c, right? And that's a wonderful property. Unfortunately, we don't have that. In Z10, however, we know that 5 times 2 is what? Z10. 0. 5 times 4 is 0. So 0 equals 0. Yes, but 2 is not the same thing as 4. So you can't just do this cancellation like you want. Okay. So that starts to hint at why division is kind of giving us a hard time already. I have two things equal. I can't just divide or cancel them out and somehow and still have things equal. Somehow that's breaking things. But we can still have a definition like we want, just like we had with subtraction. What should a divided by, that's a slanted for divided by. What should a divided by b be? We'll have a divided by b should be the unique integer x such that x times a equals b, right? I have that backwards. X times b equals a. right? So maybe this definition will work. We'll make it the unique x such that x times b equals a. So let's pretend that that's our definition for a second and see how this works. What would 6 divided by 2 be? 3. Because 3 times 2 equals 6, right? Wait a second. 8 times 2 also equals 6. So is 6 divided by 2 3 or is it 8?
Neither.
Neither. It doesn't work. We can't just do it this simply. So this gets us to the beginning of all our problems with division. And we will call it here for today. Next week we will start with modular division. It's a big old pain. I highly, highly, highly recommend you finish reading this section to get comfortable with how we find modular division and how we divide two numbers with modular arithmetic. So do that. We'll finish this up and then we'll cover 2 more sections next time. But don't worry, they're both really small. And one of them we won't even do the proof for. It was just going to be showing you how to do computations with. Kind of like solving linear systems of equations, but now you only have integers instead of real numbers. And that gives us a couple problems. But once we have division, if you understand division, it'll be easy. So make sure you understand division, read the section, we'll start there next time, make sure you understand division, and then we'll finish up the chapter. Shouldn't be too bad. Mostly I'm just hurting too much.